My name is Will Hancock, and I'm a professor of biomedical engineering at Penn State University. I've been here since the year 2000, and I have been studying kinesins since 1994. I got into them because I was studying muscle contraction for my PhD, understanding heart muscle, and these were a different type of motor. And it was very new and exciting then. And so I've been working on kinesins since then. I've been working on KIF1A. Let's see, maybe almost 15 years, 12 years, and quite intensively for the last 4 or 5.
At a broad scale within the scope of kinesins, what is it that your lab is studying now?
Well, one of the things that I've been interested for the whole time of my career studying kinesins is what we call the interhead coordination, or basically, if we think of them as walking along the microtubule, the fact that they have 2 feet and these feet coordinate their activities, and they need to go through cycles of attaching to the microtubule and detaching, but doing that out of phase so that there's always one head bound at all time. That's how they carry their cargo. And so the timing of that and the communication, which we call mechanochemical communication between the 2 heads, is just an incredibly fascinating question, because it's just an enzyme, but the 2 domains are communicating with each other, and that's really integral to their function. So that's one of the big things that we're studying with all kinesins. We want to understand, fundamentally how, when they use ATP and they go through their enzymatic cycle, how they're able to produce conformational changes that directs the walking, and how different kinesins like KIF5B, KIF1A, KIF3A, there's 45 in the genome, how they're tuned differently. And so for KIF1A, it's interesting that they're particularly fast and they're very processive, meaning they stay on the microtubule really well. And so we're doing a lot of biochemical experiments to try to understand that. And in collaboration with Jonas Pirpasopoulos and Mike Ostap at University of Pennsylvania, about 3 hours away, we're studying the mechanical properties of these same KIF1A motors using optical tweezers.
And that's a great lead into my next question, which is about tools and techniques you're using. Could you briefly describe how optical tweezers work, what that technique entails?
So optical tweezers are a way of manipulating molecules. And the idea is that light photons have momentum. And we don't really think of photons that way normally, but if they are focused in such a way and that they're traveling through a bead, and the bead is acting as a lens, because they have momentum, the lens bead is changing their direction, and so that requires a force. And so that means, just from basic principles, that the light is causing a force back onto the bead or the particle. And so, because the forces that these motors generate are very small, in the piconewton range, the forces that light can generate are, as long as you have light from a laser and it's coupled properly, are in the same regime. And so the best analogy is a tractor beam from Star Trek, where the ship sends out a beam and it traps another ship. Conceptually, that's what they're doing. So we are trapping a bead, and then generating force on it, and so then the motor is generating force against it, and we can measure those forces, we can measure those displacements. And so it's a sophisticated way to measure the stepping dynamics and to measure the amount of force that can be generated by these motors. So another technique that we use is what's called gold nanoparticle tracking. And so the question that we're asking is, we want to understand how the heads are interacting with one another and how their cycle occurs as they're walking along the microtubule. And they take more than 100 steps per second. And so that means each step takes just a few milliseconds. And so it's all very fast. And because they're small, then the displacements that we want to see are very small, like nanometers, 10 to the minus 9 of a meter. And so what we've been able to do, building on work that was developed by other people, is to attach a really small gold nanoparticle. So it's a 20 nanometer or 30 nanometer gold nanoparticle. So it is actually bigger than the head, but because of the scaling of forces down to the nanoscale, it doesn't perturb the head. But there's a property of these gold nanoparticles in that they scatter light really well. And so we can visualize, by shining light on the motor, the gold particle labeled motor, we can visualize these gold nanoparticles. And we can do so at 10,000 frames per second. And so we can measure the position of one of the heads every 10,000 times per second as it's stepping along the microtubule. And we can do that with the precision of a couple nanometers, which is the size of the displacement. And that has really opened up new ways of understanding the cycle, understanding the hydrolysis cycle, understanding how the two heads coordinate their activities, and really understanding the guts of the motor, of how they work. So that's a really exciting technique that we use in my lab quite a bit. And we've done it for other kinesins. We're currently working on it with KIF1A, and we have some preliminary data, but we're still working out the kinks. So hopefully over the next year or so that we'll generate that data, and that work will come out.
How do you see these kinds of biomechanistic questions fitting into the larger questions of how do we find treatments or understand diseases like KIF1A associated neurological disorder?
So the work that we're doing is really down at the molecular level and understanding these motor mechanisms. We want to understand the specialties of this motor and understand some of the subtleties of how they interact with microtubules and how they work with other motors to carry cargo. Because in the end, the mutations that lead to CAND disorders are affecting the motors and how they're walking, how they're interacting with the microtubule. So we're really trying to understand how it normally works, and then we can introduce those, we can make those mutations in the motors that we use. We're using recombinant DNA technology to make recombinant motors, and so then we can understand how those mutations change the motor properties. And then we want to go one level up to the cell and say, okay, if this is what's wrong, then when they're carrying a cargo through the web-like networks of the cytoplasm and the axon and working with other motors, how is that going to affect how they carry their cargo? And then how do changes in how they carry their cargo, is that going to affect the state of the neurons, the health of the neurons? And then how is that going to affect the body and do it, and over time, over years of development like that. And so it's a multiple scale problem, from the molecular to the cellular to the tissue to the organism. And then it's multiple times. So we're looking at things down at the millisecond scale, and then you have seconds, and you have hours and days and weeks and months and years. And so it takes a village research wise. It's really important that there's a community of researchers studying using different techniques at different scales and trying to bring that all together. And we hope that by understanding it at the different levels, we can really get a clear picture that will give us new ideas about how would we then design drugs that would try to correct these defects or compensate for them in some way. And so I think, taking that holistic picture and then trying things, with different compounds, and that's a really important part of it too, to see how we can perturb things.